Well, welcome everyone. And this presentation is designed to help people clear up a lot of misunderstanding that exists about electromagnetic field and what they do. Because once you understand electromagnetic field, you will understand a lot about electricity itself. So the first question is, what are electromagnetic field? The short answer is electric and magnetic fields zipping through space at the speed of light. Now, this is a short answer that needs a lot of explanations. Most people do not understand fully what it means, and that generates so much misunderstanding. So we have to step back a little bit and go back to the basics. And to help us with that, let's look at myth number 1. Ions can flow through a wire. We hear that all the time. And you'll see probably in some questions that people think, well, can ions from the earth come through my body? And, is that how earthing works? No, there's no ions. Everything's about electrons. So in order to understand that, we have to go back to the basics, which is the structure of matter. What is matter composed of? It's composed of atoms. And every molecule is made of a number of atoms. So just a reminder for everyone, an atom is made of a nucleus, and which has 2 particles in it. In general, a proton, which is charged positively, a neutron, which is neutral, and zipping around the nucleus are electrons, which are smaller particles, lighter particles that are charged negatively with the exact opposite charge as a proton, which is positively charged. So what keeps the electron zipping around the atom is actually an electrostatic force that exists between the electrons and protons. Electrons and protons attract each other. And so that creates the force that maintains atoms together. So it's really the basic force in the universe that maintains all matter. It's an electrostatic force. For example, and people talk about ions, what is an ion? An ion is an atom and molecule. See, this atom is neutral, has as many electrons as protons. Neutrons are neutral, so they're not a problem. But let's say that you're able to knock off an electron from this atom. Then what will happen is that you have one more positive charge than negative charge. And when you see the atom from a distance, it will behave like a positive charge. It will be a positive ion. That's what we mean by positive ions or ions. Now, you may have circumstances, especially in certain molecules, where you can have an additional electron or 2. In that case, then you have more electrons than protons. And now your atom is become negatively charged, and that becomes a negative ion. Now, in most of the atmosphere that we're breathing, there are positive ions are much more present than negative ions. That's why when we get close to certain place where there are negative ions, we feel good. Like you go to the ocean, for example, you breathe the air next to the ocean, there's a lot of negative ions there. If you go to a certain forest, also you have lots of negative ions. But in general, we breathe positive ions. And that's not a problem, that's the way we design. But you will see that too much positive charge in our body is not so good. Now, to get to the next level of understanding here, so okay, we have atoms. And then they group together, they form molecules and solids. I give you an example here. The crystalline structure of a table salt, which is sodium and chlorine. So these atoms link together, the sodium being the big red green one, and they link together by what? By exchanging electrons. Again, what maintains the entire structure of the crystal are electrostatic forces between atoms. And it's the same for every material. They're not have crystalline structure, but they all have atoms that are linked like this. And so you can see now that the protons and neutrons, which are inside the nucleus right here, they are bound to the structure of the material. Without them, the crystal or the material will dissolve, will disintegrate. So they cannot move. What can move are the electrons. In metals, for example, electron can be shared anywhere along the metallic structure. So that's why we use them as conductor. That's what they call conductors. And so a copper wire, for example, when it's used in an electrical circuit, then electrons can move through it freely. And that is, as I said, a conductor. But no ion ever flow through a wire, because the ions, if there were any, they will be bound to the structure. And that was a problem with DC currents. Like, you know, in the old days, they were using DC currents to power homes. They found that the copper wire become brittle and they fall apart. That is because using a copper wire with a DC current, the flow of electrons at some point take away some electrons from the structure, and you get a brittle and wire. So AC is much better for that, because the electrons just move back and forth. Anyway, this is a little technical, but just to let you know that ions can never flow through a wire. It's only electrons. Every current that flows in your home, every device, your computer, everything, cell phone, it's all about electrons. So I hope we nail this one, and you understand that if somebody start talking about flow of ions through your body or through any solid object or any circuit, just go away and talk to somebody else, because these people will not be able to shed any light on this subject matter. In fact, they're going to just confuse you. Okay, so let's go a little deeper. Our goal is to explain what is an electromagnetic wave. So let's go deeper into the electric field. As I said, positive charge has a positive electric field around them. It goes, the lines here show the electric field going outward. These electric field lines are actually representing, if I put a little positive charge here, it will be repelled and going away from the positive charge here. That's why the arrows are in this direction. In the case of a negative charge, the arrow goes in, because a test charge that we'll put here will be attracted towards it. So these are really lines of force. That's what an electric field is. Now you put the negative and positive particles next to each other, and it's like they like each other. And you see the field lines of one complement into the other, and you'll have an attraction between the two. And the attraction is going to be right in the shorter distance between the two, where the density of field line is greater. So this is attraction. But any positive charge against a positive charge, or a negative charge against a negative charge, you'll always have repulsion. Okay, so that's how the electric field works. So two charge of opposite sign attract each other. Two negative charge repel each other. Two positive charge repel each other. That brings us to myth number 2. The electric field and magnetic field are pretty much the same thing. I see often in videos people using magnets to try to illustrate how electric field works. No, that's not correct. A magnetic field and electric field are very different beast entities, even though they work a lot together, and I'll show you how. They are very different. The electrostatic or electric field is present everywhere. That's the basis of what the magnetic field comes from. A way to use those electric charge. I'll talk to you about that later. Sorry. So let's see what the electric field does in real life. So let's take, for example, here it says a plastic rod. It could be a plastic pen, pencil. And you have animal fur. When you rub one against each other, you get that the plastic will steal electrons from the fur. The fur will become charged positively, and the electrons will jump on the plastic rod, and the plastic rod will become negatively charged. Sorry. So now if you take this plastic pencil and bring it close to pieces of paper, these pieces of paper will be attracted toward it. It's an electrostatic attraction. It's not a magnetic one. It's because the pen is charged negatively. And the piece of paper, remember, in the piece of paper, the protons inside the nucleus cannot move, but the electrons can. And so the electrons are repelled away, and the nucleus, positive nucleus, are getting closer to the edge of the paper that is closer to the pencil, and that creates an electric field and an attraction that is sufficient to overcome the gravitational force. Anybody can probably has tried that. It also causes your air, for example, when you rub against a carpet to stick out, or when you have clotting in a dry climate, you have sparks sometimes happen. Just like this one, when you try to touch a doorknob after walking briskly on a carpet, you may be zapped like this, like a short lightning happening between your finger and the knob. By the way, walking on a carpet like that, you can charge up your body up to 30,000 volts. I know it's a lot of voltage. It's way more than 120 volts that we have on our circuits. But what saves you is you're not grounded and you have touching nothing. That's why you have this thing when this discharge between you and the knob when you are charged like that. And actually what happens here is that it's the doorknob that gives you electron. That's what the charge is. And it is happening because an electric field is created between your fingertip and the doorknob. And it becomes so strong that the electrons have to move along the electric field and get to your body. This is the same process actually as lightning in a thunderstorm, but at a much smaller scale. I mean, imagine how much voltage need to be created in the clouds, between the clouds and the ground, for an electric discharge of what, 10,000 feet high can happen and zap through the ground. And that's how actually the earth gets charged, is that the clouds in the lightning give electrons to the surface of the earth. And that's why we feel when we're next to a lightning or a thunderstorm and there's lightning happening, we feel like, oh, there's electricity in the air. Yes, there is. That is true. So magnetic field is totally different beast. Here's an example of a sheet of paper with iron fillings on it. And when we place a magnet, a bar magnet underneath, what will happen is that the iron, which is a ferromagnetic material, so that means it can sense magnetic field. Most material cannot and will get, because they're not ferromagnetic. And I'll explain a little bit later what is special about iron. So in any case, so you have here the iron fillings that actually follow the line of force of a magnet. And if you notice, we have a north pole and a south pole, not a positive pole and a negative pole, because this is not electricity, it's magnetism. For example, if you were to put your pen right here, that is charged negatively, the pen will not be attracted towards the north pole or the south pole. It's not the way a magnetic field works. If the electric charge, if you move the pen, you will see that the pen will have a force pushing it around the magnets, not towards the pole. It's totally different thing. The magnetic field is totally different thing as the electric field. So in recap, let's look at the difference between electric fields and magnetic fields. So, sorry. Electric field arises when from electric charge. So they're always present. As soon as you get an imbalance between the number of protons and the number of electrons in the material, you get electrostatic charge, and you can sometimes, feel it. The strength of the electric field is measured in volts per meter. You might see that in some books. The electric field is present even when a device is switched off and there is no current. And most building materials shield electric fields to some extent. Very easy to shield electric field. On the other hand, magnetic field arises from currents, electric charge in motions. Now people say, well, what about magnets? Well, if you look at microscopically at magnets, they actually have electrons that turn around their nucleus in a certain organization that they align. It's like small, an atom is also like a small magnet. But in certain element like iron, they align themselves and they create from millions of small currents around atoms, they create a big magnetic field, which is a magnet. So even in magnets, magnetic field arises from currents. So their strength is measured in ampere per meters. You'll probably never see that. Most of the time you hear about a related quantity that is the magnetic flux density, which is in microtesla, millitesla, a Gauss, or milligauss. For example, the magnetic field of the Earth is 0.5 Gauss, or 500 milligauss. It's quite a small magnetic field, and yet it has physiological impact. If you are deprived of the geomagnetic field, you will feel it after a couple of hours. Magnets have much stronger magnetic field, and we can talk about microtesla and millitesla because 1 Tesla is gigantic magnet. It's 10,000 times a Gauss. So 1 Tesla would be 10,000 Gauss. Very, very strong magnet. 3, magnetic field exists as soon as the device is switched on and current flows. No magnetic field exists before that. 4, magnetic fields are not attenuated by most materials. They can go through, copper, they can go to walls, they can grow to almost anything except ferromagnetic materials, such as iron, nickel, and cobalt. And all these 3 actually are used to make magnets. The very strong magnets are made normally of an alloy of nickel and cobalt. Okay, that's very good. So now, that brings us to myth number 3. EMF contain electric charges and can create a current that can zap you. You hear that a lot of people who are building hygienists, and they don't want you to be grounded in a house because they claim that because of the presence of electromagnetic field that are coming out of the wires, ions are created. Again, the ions are coming up, and that will flow through your body, which they can't, obviously, and that create a current that will zap you, and that's very dangerous. Nothing can be further from the truth. If somebody tells you that, just turn them off, look at somebody else for counsel on this or information in this field, because these people, they don't know what they're talking about. There's no electric charge in electromagnetic field, first, and second, ions cannot flow into a body, even though the body has some liquid, and that means that it's possible if you get inside the body to make ions move, the outside of the body is solid, and a current, you know, can flow only if somebody has electric charge, but an electromagnetic doesn't have any. So that means now we are ready, I think, to go to the next step and see how electromagnetic fields are generated. They're generated, most of them are generated by antennas. And here you see an antenna, which is basically a wire that has a current that flows back and forth. You have electrons moving back and forth on this wire here, and that creates an electric field in blue and a magnetic field in red, and it goes in the back here and becomes yellow, but they are perpendicular to each other. So if the electric field is in this plane here, the plane of the paper, the magnetic field will be in the opposite plane, the plane that is 90 degrees from the paper, from this piece of paper. And these two will flow and will zap through space at the speed of light, which is extremely fast. Let's look a little bit more closely to what happens. So here we have the electric field. So let's pretend that this is the antenna, and the electric field is generated along this vertical line. So as the electron move, it generates magnetic field that propagates, and it goes like this. It goes up and down and up and down. And what is now the relationship? Why do we have a magnetic field also? It's because a varying electric field, when the electric field changes, the law of electromagnetism showed that a magnetic field is generated by a varying electric field. So the varying electric field induced in space at 90 degrees in the horizontal plane here, a magnetic field that will also be changing. But a magnetic field changing also produces an electric field. And so now the electric field will produce a magnetic field. And you can see the interplay between the generation of the electric field and the magnetic field, because they vary each other, they recreate each other. And this whole process travels at the speed of light, which is represented by the letter C here, which is very fast, 300,000 kilometers per second, 186,000 miles per second. How fast is that? Well, to give you an idea, a ray of light can do 7.5 times around the planet Earth in only 1 second. That's how fast light is. And all electromagnetic fields go at the same speed. For example, if you shine a light to the moon, the light takes about a second to get there. So that gives you an idea of the distance of the moon. And the sun, the rays that we see from the sun, when we look at the sun, has come to us 8 minutes before. The sun is 8 minutes away in terms of light speed. That is 480 seconds. That means that the sun is 480 times farther away from us than the moon. So, but yet they look the same size. So if you look at, if you were to bring the sun as close to us as the moon, it will fill the entire sky. The diameter will be 480 times that of the moon. We will be burned out, of course. Just to give you an idea of how fast is the speed of light. Now, you hear often about electromagnetic field, about, oh, there is a wavelength of 10 microns or whatever, or the frequency is 5 gigahertz. So let's get into understanding that. This comes from trying to characterize the electromagnetic wave. For example, there's something called a cycle. A cycle is when an electrons move all the way down and go back up you know, and start again the same cycle. So here, like for example, the electron, this is the maximum of the electric field. It goes down and then comes back up. Now the distance that the electromagnetic wave has traveled during that time is called the wavelength. It's represented here by the letter lambda. Let's look a little more closely here at this. Let's say that you have, let's say, a wavelength, and we follow it for 1 second. And we have here a wave, electromagnetic wave. So let's say that we're looking at the electric field. So it goes up and down and goes back to 0. That's 1 cycle. We can start here, down and up. We can start anywhere as long as we have a full cycle. And then it starts again, up and down. That's a second cycle. So that means that this electromagnetic wave has done 2 cycles in 1 second. So that's the frequency, a frequency of 2 cycles per second, which is also termed 2 hertz. That's where the term hertz is. The amplitude here is the strength of the electric field. The more powerful the antenna is at emitting, you know, electromagnetic wave, the bigger the amplitude will be of the electric field, and also the magnetic field that will be generated from it. But let's say now that I take this electromagnetic field and I have another one that zip, you know, that up and down twice as fast. So instead of having 2 cycles, we have 4 cycles in 1 second. So the frequency will be 4 cycles per second or 4 hertz. But you can even see that the wavelength will have to be shorter. And in fact, you can calculate that the wavelength will be half of what it is now. So that, interestingly, the product of the wavelength by the frequency is a constant. Here you have lambda, which represent the wavelength. And you have this letter Greek nu, which represent the frequency. And you multiply the 2 by them, and you get what? The speed of light. So that means that you can characterize any wave by its frequency or by its wavelength, and you immediately know the other. So if you know the wavelength, you're in the microwave region. Well, you can immediately calculate from this equation what is the frequency band that we're talking about. So this is very simple, but yet a lot of physics in that. If you understand that, because everything is made of waves and vibrations. And so these very basic concepts will lead you very far in understanding, you know, about the nature of reality. So just for your information, sound, people think sound is in the same frequency of some electromagnetic field. They might be, but it's a totally different beast. Sound exists only when there are atoms and molecules in the environment. No sound in an empty space, while electromagnetic field can travel in empty space for billions of miles. Sound needs air or a medium with atoms. For example, here you have a speaker and you have a membrane that moves back and forth. That creates zone of compression in the air, zone of rarefaction. So we have increased pressure, decreased pressure compared to the normal atmospheric pressure. And that travels at the speed of sound, which is much slower than the speed of light, but it's still pretty fast. About 1,100 feet per second. So this comes to your ear, and what's going to happen is that it's going to make your ear drum vibrate, and then that's what's going to be detected by your nervous system. And air is a good medium for sound, but if you are 100 meters or like even 100 feet from someone, you need to yell pretty strong to be able to talk to a person. Well, materials that are more density like water, the sound transmits much easier. a whale can talk to another whale about a mile distance away. And in solids like wood, it's even faster and even easier. And best is metals. Sound transmit so well. But that was just an aside to let you know, don't confuse electromagnetic wave with sound wave. It's a completely different thing. Now let's look a little bit at the electromagnetic spectrum. So, I mean, the frequency, here you have on the left side the frequency, and you have the wavelength. Again, the product of the frequency by the wavelength will give you always the speed of light. So they are related. But for sake of completeness, I took a scale that has both of them. And so you can have a great variety of frequencies. I mean, from 0, which is a static electric field with no magnetic field, to all the way through gamma rays with a frequency in the billions of cycles per second. So let's start at the bottom, the long waves here. Long waves are generated, for example, very low frequency, like the 60 hertz of your house will generate long waves, or the 50 hertz, depending where you are. Very, very long wave of 50, let's see, you can have a wave at 60 hertz of about 5,000 kilometers. That's how long these waves are. So when a wave leaves your wire, there's so long before it needs about 5,000 kilometers above before you get one cycle. So then the cycle go up very quickly, 1 million, and then you get to the radio waves, which like AM, FM, and now you have in the 100 megahertz. So that's 100 million hertz. And so all the way to 1,000 megahertz, which is 1 gigahertz, which is 1 billion hertz. And it keeps going up. So after radio, TV, we have the microwave, which will be the origin of interest, because most of the Wi-Fi, wireless stuff today, 3G, 4G, 5G, we're going to talk a little bit about that, are all in the microwave region. And then you have faster than that, I mean, with higher frequency, you have thermal infrared rays, which we feel as heat. The sun, when the sun is heating our skin, the heat that has been transferred for 480 seconds from the sun to us is actually infrared light, which we don't see. And then you have this minuscule part of the entire electromagnetic spectrum that we call the visible. That's the only thing that we can see between 400 nanometers and 700 nanometers. Nano means 10 to the minus 9. So that shows our short visible light, the wavelength of visible light. And the frequencies are so high, they are in the thousands of billions of hertz. So after that, you have the ultraviolet. Normally the ultraviolet also has 3 bands also, A, B, and C, which the A closest to visible. But the more they go in frequency, the more damaging they are. And then you have the X-rays that are used, for example, by dentists or doctors to see your bones and your teeth. Well, at that point, these are so energetic that now we're talking about rays, and gamma rays are even more energetic. So notice that above the visible, it becomes rays, and below the visible, it's waves. That is because this is a quantum physics effect that was not predicted by classical physics. Is that when the wavelength gets short enough, the electromagnetic wave bunched up into particles that we call photons. And this effect starts to be noticeable in the visible spectrum, where both the particle aspect or the frequency aspect can be seen depending on what type of experiment you design. There's a lot of information you can find on the internet and books about what is the nature of light. Is it a wavelength? Is it a wave, or is it a particle? Well, the dualistic notion, that the duality, that principle that Niels Bohr brought to physics was that it's both. We still have to clarify that, I think, in my opinion. But then after that, they become like little balls. Like when you have an X-ray taken of you, you have these little ball of electromagnetic energy that are shoot to you, and they have much energy. These above the visible are called ionizing radiation. They can create ions. They can knock off an electron out of the atom or the molecules. They can damage your DNA. So they are very, very strong. So try to get as little X-rays as possible in your life, because they say that it's cumulative to some extent. If you're grounded, your body will have extra capacity to heal even from that. So with that said, let's go to look a little bit closely to the microwave so that we understand what are 5G, 4G, etc. So here you have the frequency band with the low side around 700 megahertz here, and all the way up to 300. I don't even know how to say that. So many hertz here. That is, you have terahertz, petahertz, and exahertz, which are like 10 to the 18 hertz. So many frequencies too high. And you notice here you have the ionizing radiation band and the non-ionizing radiation. Now, some agency says, okay, only ionizing radiations are dangerous. So we should be careful about these. Non-ionizing radiation are not dangerous, which is, of course, not true. And we'll go a little bit over this in a moment. So 700 megahertz, you can have TV, but you can have also some of these bands that are used for 5G. So we have 2G, 3G, and 4G, which are right here between 200 gigahertz, maybe 2 gigahertz, sorry, or even 1 gigahertz to about 2.5, 2.63 gigahertz at the max. And what is the difference between 2G, 3G, and 4G? It's just that the technology got improved. A 2G cell phone was a bulky thing that looks like a walkie-talkie. And then they got better, but at the same time, the electronics become more sophisticated in being able to send more data at the same frequency. And then you have 4G, which is more like around 2.6 gigahertz. So all of these are just improvement in the same energy band. I just want to show you here that it comprises the 2.45 gigahertz band, which is microwave that are used into your microwave oven. It just happened that the technology is well known for this band. So they made Wi-Fi also the same frequency, and also Bluetooth is at 2.45 gigahertz. Isn't that interesting? So in this region, you have an effect that is similar to a microwave, where you can heat water with these electromagnetic wave. We are 70% water. So, I mean, it would be surprising to me that they do nothing. Of course, they don't have the same power than they are in microwave ovens. They're much, 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 much less. But still, you know, it's not reassuring that we use the same wavelength as those of a microwave that actually cook your food because of the presence of water in it. So 5G is very different beast, much more complex than 2G, 3G, and 4G, because in 5G, they plan to use 3 different bandwidth. The extremely high, the 5G airwave, which actually are not possible anymore. The FCC has already granted the 24 gigahertz band to AT&T for most of the country. And some other network are planning to use 28 gigahertz. China is planning to use 28 gigahertz and other bands. And these are the bands that will give you the fastest data transmission. They can give you data transmission as being recorded at a little bit above 1 gigabyte per second. Very, very fast. But there's a problem with these. The wavelength is so short that it does not penetrate. So now when the electric field is blocked, like they are easily blocked by anything, the wavelength is too short. The magnetic part of the electromagnetic wave does not have enough distance to move out, to move out of the material and regenerate the wave, which is what happened. When you have longer wavelength, like here, this 5G middle band between 3 and 4 gigahertz, and this lower one, the wavelength is long enough so that when the wave, the electric field is stopped, the magnetic field goes through, and because the magnetic field is long enough, goes through and regenerate the wave on the other side of the wall. When the wavelength is too short, it's not happening. I mean, even the leaf can stop those. So those bands are planned to be used outside in populated areas like a busy street in downtown, or in places where you have lots of people, but there's nothing in between, like a big stadium, for example. And also outside, for example, for smart cars that will be able to use that, because there will be many antennas out there that will guide the cars. But for when you are in your home, this is not what you have to fear. It's not going through. It's not happening to you. So they need another band that is able to transmit high data and at the same time going through your wall. And that's why you have these 3 to 4 gigahertz band that is going to be the mid band for 5G. Because although it doesn't have high data transmission capability as the high frequencies here have, they're still very high. They still can go 10 times the normal 4G right now. But in some places, they also plan to use lower bands, like T-Mobile now advertise on the TV that they will have blanketed the whole of the United States with their system. But the system that they're planning to use to do that is at 600 megahertz. So it goes through everything. And although it's not going to be much more, actually, it's not going to be faster than the 4G, it's in preparation for having then the next bandwidth, which is this one here. And maybe also the next bandwidth. AT&T is proceeding the same way. They have the 800 megahertz band. And they're starting with that. So you can see here that in reality, in your home, the only difference is that because they want to have higher frequency and higher data transmission in the mid-band, which is a little higher than, the 4G, they will bring the transmitter closer to your home so that more is coming through the walls, so that your cell phone can have 10 times more data than it can have right now. So, and people worry about these antennas outside, but how about the antenna inside? Your cell phone is an antenna itself. So it receives information from the antennas outside, but then when you speak on the phone, 500 milliwatts of power is going out. This is the power of your cell phone. About half a watt of energy is transmitted outside. So the big transmitter is right here in your hands. It's your cell phone. So it would be prudent, to keep it as far of yourself as you can. because again, these work close to the microwave region. So this is just prudence, you see. And while I'm saying all this, because people are asking information about this, you can see that 5G is no different than 4G in reality in terms of the damaging effect, except if you are outside in the very high band, which will be very powerful bands because they will be focused on you. The 5G at this frequency above 20 gigahertz is a very different beast. It's focused beam of energy. But in general, if you're a healthy person, you still don't have to worry about this. If you're grounding yourself every day, keep your cell phone out of your pocket, put it in your purse or carrying it, you know, away from your body. Even if you have it like a feet away, it makes a huge difference. Use earplugs with a cable to connect to your phone, to talk to your people. There are ways also to get rid of the wireless, the Wi-Fi. You can use cables, which is what I do. And you put a cable is actually faster than Wi-Fi and it's safer. So you can do these things to mitigate the effect of these electromagnetic field. And I always work grounded on my computer. And but if you're a healthy person, you don't have, and you ground yourself every day, you will not have any problem with, you know, the precautions, simple precautions that I've been talking about. There are some people who are electromagnetic sensitive. So they will feel these fields. Just being inside a home, they feel the buzzing sensation. And so they say you cannot ground because you're feeling this buzzing, because you have the EMF. You can ground. You will still get benefits. It's just unpleasant. So for you, but you still need grounded. In fact, if you are electro hypersensitive, or if you have any other, you know, most of the disease are due to inflammation in your body, cardiovascular disease, most cancers, Alzheimer's, you name it, autoimmune problems such as diabetes, arthritis. All of these things are immune-based. If you get grounded, you get your immune system working to the max. You get your body to be relaxed and so be able to regenerate itself. You charge up your battery into your mitochondria, which are really the batteries of your cells. There can be 1,000 or more by cell of these little batteries. And you're making all the chance of your side, you know, of staying healthy if you do that. Of course, you need good nutrition. It's not a panacea where you do only everything and I can go and do anything. I can drink, you know, 3 bottles of wine every night. I can party non-stop, eat any junk food I like, and everything will save me. No, it's not like that. I can tell you that you still need to have good nutrition. You still have to have a good lifestyle. But everything will go a long way in helping you. And other things that, you know, even it's very difficult, for example, in the world we live today, you know, many people, we have an epidemic of diabetes. And these people are not bad people. Many of these people don't eat differently than normal people do. You go to McDonald's and stuff like that. But still, it's not congruent with a good lifestyle for us. Because all processed food are charged positively. So we are fed all the time with positive charge, positive charge. When you grow a vegetable in your home, or in your home, in your garden, it's been in contact with the earth. It's charged with negative energy, the electrons, not the ions. Maybe there's some ions, but the electrons have been charging of the earth, has been charging that. And when you eat that, you have a live food. And in fact, you can buy a little device called an oxidation reduction potential device, which is just like a pen. Stick it in a fruit, and if it goes negative, it's a good fruit. If it goes positive, it will deplete you of energy. So we need to ground ourselves the best way that nature intended for us to be healthy. We need to do it every day. It's like a vitamin. If we miss it, we're going to suffer. You cannot ground yourself 24 hours a day for a month and say, I'm done for the rest of my life. It doesn't work that way. Have to ground every day, at least half an hour if you're healthy. If you're not healthy, you'll need more time. So, so I'm hoping that this cleared up a lot of misunderstanding about electromagnetic radiations. Understand it's not a huge threat if you know how to live healthy and be grounded. And I think that's the